Welcome back from Reading Week. This week we're going to be talking about first level analyses. I'm going to do it in a series of 3 reasonably short videos. And what I hope to cover includes introducing the whole mass univariate approach to analyzing fMRI time series data. As part of that, I'm going to talk a little bit about convolution and what we use it for and how it's an important factor in generating our expectations of the bold signal. I'm also going to talk about rank deficiency. This is a concept that comes up a lot, particularly when you design your design matrix, and what it is, how to avoid it. It's not very difficult to avoid, but it's important to be aware of it. And then finally, I'm going to talk about temporal autocorrelation and introduce some methods for dealing with it. What it means to your time series, what it means to your statistical analyses, and how we actually compensate for it. So in this first video, I really want to talk mostly about the general linear model, introducing this mass univariate approach within the context of the general linear model, which we often will refer to as the GLM. Some of you may very well already be very familiar with the GLM from previous statistics courses. And nothing I say today is going to be fundamentally different than what you've heard previously. But for some people who haven't necessarily seen it all before, this may be the first time that they've been introduced to it. So I will introduce the idea. I'm not going to go into it in incredible detail, but I will give you a little bit of a feel for the math so that you're familiar with it and you've seen it. The important thing to start with is that the data that we've acquired during an fMRI series is a time series data set. That is to say, we kept acquiring volumes time after time, every repetition time, right? So we didn't just acquire one and then something else at a random time. There's a fixed interval and it's constant. That's what the data that we're looking at are. And as we've talked about in previous weeks, we go through a series of image preprocessing steps that include realignment, typically registering the data to a standard space kind of template, as well as some form of spatial smoothing. And it's those preprocessed data that are going to form the input to our statistical analysis. And what we're going to do is we're going to take this analysis on a voxel-wise level. That is to say, in the 3D space that we've collected from EPI data that is our brain data, there may be 25,000 individual voxels in there, right? Each one a 3 by 3 by 3 millimeter cube of brain tissue. We're going to analyze each of them individually. And this is that mass univariate approach. That is to say, each voxel is its own thing. It's going to have a univariate analysis. The fact that it's next to another voxel is something that is not going to come up in our statistics at this point. It'll definitely play a role when we talk about statistical inference. And of course, at some level, they aren't really independent of each other for all of the smoothing that we've already done to the data. So some of the interpolation that we've done, as well as the external smoothing kernel that we've applied, means that voxels that are next to one another aren't independent of one another. Nonetheless, we will treat each of them as independent, and this is that mass univariate approach. Okay, so what we're going to do is we're just going to pick a single voxel, and let's just say this is a time series of the bold signal in that voxel. If we were expecting something along this line, something like a smoothed block design, then what we can do is we can compare the actual data that we have to our model of what we expected, our expectations, using the general linear model, right? And using the general linear model, we're going to generate a set of statistical parametric maps, or SPM. That's where the software gets its name. These are known as statistical parametric maps, and we'll go into why in just a minute, but that's where the software name comes from. Okay. So if you haven't seen the general linear model before, this is the equation that we're talking about. And it's very, very simple. I'm going to try to keep all the math in this module fairly simple and very linear where I can. Where it is not, where it's intrinsically nonlinear, I'm going to try to make everything graphical rather than get you through the details of the mathematics. But for the general linear model, the important thing is we have some data. And in our case, this is going to be literally the bold signal that we've recorded from this voxel that we're analyzing at this point in time. That's the data that we're looking at. We're going to have a model. We're going to have an expectation of what we should see if this piece of brain tissue is responding according to the experimental paradigm that we've designed. So this is our model, our expectation of what we should see. Then we're going to have a set of parameter estimates. In the simplest form, we're going to have one parameter estimate, which is how well does this model fit this data, right? And that's what the beta here is doing. And then finally, we're also going to have what we're going to call residual error or variance, noise, right? So anything that doesn't fit the model is just noise. And that's all this equation does. This is a linear equation because, as you can see, the most complicated term is are two values that are multiplied together, which is a linear model. The model, x, is multiplied by the parameter value beta, and that's our linear term. We're going to expand it a little bit, still keeping it very linear, but this is the basic equation that we're going to be using throughout this week and throughout the module. I should say, there are more complicated ways of doing this, right? So there are lots of other ways of analyzing fMRI data. From my perspective, the most fundamental is understanding this mass univariate approach using the general linear model, and that's what we're going to cover in detail in this module. If we had, say, a second term to go through more complicated fMRI analyses, fMRI designs, then we could go into other techniques. So there are things like independent component analyses that can be used to look at your fMRI data. There are what are known as multivoxel pattern analysis methods, which are essentially basically machine learning kind of approaches. And there are others. There are wavelet analyses. There's a whole slew of these. And they're all valuable and they all play a role. But jumping to those without understanding the fundamentals of the general linear model, in my opinion, is a mistake, which is why this is what we're going to focus on. I'm not suggesting that those other things aren't valuable and helpful. I just don't think that that's the right place to start. Okay, so this is just a really simple example. I think it comes from the Poldrack book, where they're just trying to illustrate the relationship between, for instance, a husband's age, which is shown here on the x-axis, and that husband's wife's age, which is shown on the y-axis, right? So in this case, we can fit a general linear model to this, where the y value is the wife's age. Those are the data points that we have. Our model is going to be the husband's age. We're just going to assume that the relationship between the husband's age and the wife's age is very simple and can be modeled via a line, right? So that means that our x value is the husband's age. That's our model. And the parameter value, beta, is the slope of this line. And you can see it's roughly a 45-degree slope. That is to say sort of a one-to-one relationship. That is to say that if you are a 60-year-old guy, odds are your wife's going to be somewhere near 60 years of age. And if you're a 45-year-old guy, your wife's likely to be about 45 years of age. Now, that's true on average, and you can see that through this line. But of course, there's also noise. There are people, and one here shown with a 70-year-old man with a sort of 57-year-old wife would be the point at the bottom of that sort of bracket under the epsilon. All of those are the variance in the data, the noise, the residual error that are going to go into the epsilon term. Okay, so this is just a very, very simple example, but we can do this in a more complicated fashion using the actual fMRI data. Right, so as I said, let's think about the data. These aren't the raw data that have come out of the scanner. These are the raw data after pre-processing. So we've already gotten rid of the dummy volumes. We've realigned the data to deal with some of the head motion effects as best we can. We've typically normalized the data to some sort of standard space, although when you apply that step varies a little bit depending on different software packages. But in SPM, we do that before we do the statistics. And then we've also done some sort of spatial smoothing on the data. So what we're looking at this point are the pre-processed data and over time. And those are our y values. If we were to just pick a given voxel, and I've just put a little square here, and then put some synthesized data up, and just plot those bold signal values over time, those are the data that we're looking at, right? That's what our y value is. And if you picked a different voxel, then you'd have a different data set. So this is that mass univariate. We're talking about doing this on the order of 25,000 times for any given fMRI run. And it'll vary a little bit depending on how much data you collected for each person in terms of the field of view and also the voxel size and things like that. But nonetheless, the principle is the same, independent of the number of voxels that you actually have there. And the fact that we're looking at them one at a time means that it's a mass univariate approach. We're going to do this 25, 30,000 times. Thankfully, that's what the software is going to do for us, right? If you had to do all this by hand, we would never have made any progress whatsoever with fMRI because it would just be ridiculously tedious. So one way to represent the data is the way I've done it, which is just to plot it over time, this sort of bold intensity as it goes up and down. But another way is to just sort of put this into a vector, right? A vector is just a column of values that follow one after another. They've got a structure in the sense that one of them follows the one before it. So 676 is our first value, 694 is our second, and it matters that 694 is second. It's not the 9th, it's not the 11th, it's the second value, right? So there's a structure, there's an order here, and that order can be represented as a vector. So I'm going to write y as what's called a column vector, which is shown here. And then what I need to do is come up with a model. And I know what our experimental design was. So let's assume for the purposes of the lectures this week that for the most part, we're just going to be talking about a simple block design task like the kind of finger tapping thing that we've done in the past. We do 20 seconds of finger tapping, then we have 20 seconds of rest, then we do 20 seconds of finger tapping, 20 seconds of rest, etc. So we have this kind of design that's shown here in the slide at the moment. But what we know is that if that's what we're doing, we would expect a response that's sort of based on that on-off pattern, right? So we would expect a response that sort of starts out low, goes high, stays there for about 20 seconds, goes low, stays there for about 20 seconds, then comes back up, etc., right? That's the block design that we're looking at. However, we can do better than that because we know that bold signal is actually something that's a function of the blood, right? The oxygen level in the blood, and the blood system doesn't respond instantaneously to changes in neural activity. There's this delay due to the hemodynamic response function. And that's what I'm showing here. We know that if there's a focal event in time, then what we're going to expect from the hemodynamic function is that we're going to get a peak that happens sort of 5 to 6 seconds later, trails off, and returns to sort of a steady state baseline at about 20, 21 seconds after that. So that is our estimate of the relationship between the neural response, which is effectively instantaneous. It's on the order of milliseconds anyway, and the blood flow response, which is anything but instantaneous. It's slow, it's a little bit sluggish, and it's smoothed out over time. So it happens on the order of 5 to 6 seconds later at its peak response. So when we design our model, we don't want to design the model solely based on what should be happening neurally. We want to design our model to take into account this hemodynamic response function because we know that that's embedded in the bold signal. So otherwise we'd have an unrealistic model that doesn't particularly match very well what we really are getting out of the physiology. And the way we do this is to use a mathematical function called convolution. And once again, I don't really want to talk about the details of how you do a convolution. It's not super complicated, and you can look it up in almost any standard kind of textbook. But what we're going to do is essentially smooth our paradigm, our experimental paradigm, in this case that block paradigm, with this estimate of a hemodynamic response function. So what you can see here is we have an estimate of the hemodynamic response on the left. The convolution signal is that cross in a circle. And then the model of the actual experimental paradigm is shown on the right. And when you combine them, when you smooth the paradigm with the hemodynamic response function, you move from just having this block of on and off that's shown in black on the bottom to this kind of smoothed, increasing, decreasing paradigm in red that is your model of the paradigm, including your estimate of how the blood flow is going to affect the signal that you're actually recording. And just as you can write the data as a column vector, you can also write the model as a column vector. So I'm showing this as with time shown on the x-axis, so that as we move from left to right, we're going further and further in time. But we could invert this into a column vector and just put those as numbers and then show it as a x equals this particular column vector. With that in mind, when it comes time to estimate the parameters, we've got the data from this voxel in this column vector, y. We've got our model, our expectation, that we can put into this column vector, x. And we now have an equation. We have data, we have this model, and what we can now do is estimate the beta value, the parameter that best fits the two, and then anything that's left over goes into the residual error, the epsilon. Because you're doing this for every voxel, on the order of 25, 30,000 voxels, we get 25, 30,000 beta values, 25, 30,000 epsilon values, and they have a spatial arrangement. So they're not just randomly distributed willy-nilly. You can actually refer to this value having neighbors that are to the left and to its right, to its in front and to behind, and above and below it, right? It has a spatial characteristic. If we put those beta values all together in a spatial map, then what we end up with is a statistical parametric map. That is to say, the parameters, betas, that we've estimated from our statistics, our general linear model, have a spatial arrangement, so they play out in a spatial pattern that we can characterize in a three-dimensional map. That is what an SPM is. Similarly, the variance, the epsilon, is exactly the same. It's a parameter that we've estimated based on the data and our model, and we've estimated at all of these different locations, so we can map those into a file that has 3D representations of the epsilon variable at each of those locations. And you can visualize these. You can absolutely just look at a parameter size map, and you can look at a variance map. And look, in this case, the variance map here on the right is actually a little bit clearer because there's more contrast between them, high and low values. But you can see, for instance, that this is an axial slice, so the bottom of the image is visual cortex, occipital temporal areas, and you can see that the variance there is lower than it is in some of the other parts of this particular slide because it's darker. And that's simply because there's going to be a visual cue that was coming on to saying, oh yeah, now it's time to tap, now it's time to not. So that is to say there was some visual stimulus, so the model fits better, and therefore there's less noise in those areas. And you can see that just from looking at the variance map. Looking at your statistical parametric maps is a good idea because sometimes there are things like this that are very clear and you can say, yep, that makes sense. That's a good sanity check to sort of understand that I've done my modeling well. But sometimes there are weird things, particularly in your variance. And if you realize that there's some areas of really high variance, bright spots in these maps that don't make any sense to you, then it's good to go back and try to figure out where they came from. Is it some sort of artifact because of your pre-processing that's gone wrong? Is it an artifact in the data to begin with? It's a good way of catching things that you wouldn't otherwise see by just looking at your final set of results. So I highly encourage you, particularly as you're learning fMRI, to spend some time and look at your variance maps, look at your effect size maps, to just make sure that they're doing sensible things and you understand what's going on. If not, then it's definitely worth going back, trying to figure out where that anomaly has come from in your pipeline of the analysis stages that you've gone through at that point. I want to leave it at that. And the next video, we'll talk a little bit more about how we can use the general linear model in a slightly more complicated way, but to take into account the data in more realistic ways.